Hello guys, welcome again to this web series which is on machine learning fundamentals. So we are on to an important topic. We're discussing imbalance in data, and previously we had discussed what is actually data imbalance and what impact it can have on machine learning models. And in fact, we had discussed various areas where this can be very critical. And now we'll be having, in fact, some understanding and overview of how this data imbalance can be handled so that we can just get optimum results in various areas of application where this can prove to be very critical. So, solutions to imbalanced data. First of all, we can have oversampling. So oversampling is one of the ways that we can tackle imbalance of data. We can increase minority class samples to balance the data set. So this is in fact having the previous example which we had given, that we are having 950 records which are in fact representing one class, and then we were having 50 records which were representing the second class. Now, what we can do is we can increase this minority class, which is, for example, the 50 samples which are there, that is a minority class. So class 0 was in fact the majority class, and then there in the example we had taken, class 1 was the minority class, which was having 50 samples. So what we can do is, with this oversampling, we can increase the minority class so that samples which are there. And this technique includes random oversampling. There is one which is called as SMOTE. There is an adaptive one as well, which is called as adaptive synthetic minority or sampling technique is there, and there's an adaptive one. We'll be taking them one by one, all of these, but these are all oversampling techniques which will be one way or the other. We'll be discussing that in each of these schemes what happens exactly. It is increasing that minority class to such an extent so that it does not remain a minority, and the model is corrected in a way to such an extent so that it is providing us the realistic results. So primary focus of this particular technique is that oversampling will be happening. One more area which is there is undersampling. What is undersampling? We are reducing, so instead of increasing the minority class, we are reducing the majority class. This is useful when data is abundant, and then in fact the risk of losing valuable information is less, because if you are decreasing the majority class, you will be having a lot of risk that you should not be losing your valuable data, which will be having an impact on the performance or overall performance of the model. So because that can be a valuable information, and if you are losing that valuable information, it can have a significant impact on the model performance. So that, keeping that in consideration, if you are having data in abundance, that you can decrease as well the majority class, that is also going to have an impact and on the imbalanced data, and it will be to some extent it will be balancing the data. So this is one more technique which can be used, that is undersampling. And then algorithm level, cost sensitive learning and ensemble methods can be it's a combination which we have discussed a little bit when we were doing random forest. So modify algorithms to penalize minority misclassification more heavily. So it is, we can have certain modifications done at the algorithm level, which can in fact accommodate these minority classes, and we can modify the algorithm to penalize minority misclassification. So wherever we are having misclassification of minorities, it will be, so a modification in the algorithm can as well address to certain extent address this imbalanced data. So the choice of choosing the solution, which are solutions that are given there. three types of solutions. What is the choice? How we can? It depends upon the data set size. It depends upon the imbalance ratio that you are having in the data. It also depends upon the use case, the implementation area, the application area where you are applying it, the business needs which are there. Depending on all of these factors, we can choose solutions, or we can in fact choose multiple solutions as well in certain cases. So these are the solutions that we are having to tackle with imbalanced data. Now, oversampling. What is oversampling? We have discussed that, in a superficial manner. We have just said what exactly is oversampling, and there are types of oversampling as well. Now, first of all, definition: increase minority class data point to balance classes for improved model performance. Definitely, the oversampling definition itself is saying that we will be increasing, we'll be putting more values to the minority class. That means, to some extent, we'll be in fact, definitely we'll be able to balance then classes, so that we are getting an improved model performance. So definitely, it is not going to remain a minority class when we are improving it, when we are having more records. So that is increasing it. That is what our sampling means. Then types are there. That's a different thing. We'll be explaining each of the types. How that increase in minority class is going to exactly happen will be, then giving us what are different types of our sampling techniques. So goals which are there: improve model learning on minority class patterns and enhance prediction accuracy. Definitely, will be giving a better learning on the model, to the model on the minority class, so that overall performance of the model is improved. What are the advantages of oversampling? We are not losing any data. Original data set is intact. We are adding just the minority class. That means the class which was having lesser number of records. We are adding to that. We are having better minority class representation in the training. So definitely, and that will be having overall impact on the performance of a particular machine learning model. So considerations. What are the considerations that we need to just consider while using this technique of oversampling overall? Risk of overfitting due to synthetic samples. So there can be a problem of overfitting because these are synthetic samples which have been increased computational requirements. So that definitely happens. Your data set is going to increase. You're putting synthetic data to it. So the computational requirements which are there, that you need to just see. One of the types of oversampling is random oversampling. What is random oversampling? So concept: random duplicate existing minority class samples to balance the data set. So what we are doing is, for example, we are having an example of 950 and 50 records. So what we can do is, instead of 50, we can put it as 500. I'm just giving as an example. It is the same data, minority class. We are duplicating the same data and getting it to 500 instead of 50. So we are duplicating the records which are there. We can take them to 200, 100, 300, 400. For example, we are taking them to 500 so that we can balance this imbalanced data and minority class which is there, so that this ratio which was coming as 19:1, that will be decreasing, and we'll be having a good representation of minority. So the same example, it is saying before class 0 used to be 950, class 1 used to be 50. We can have, for example, after class 0, 950 and 950. So we have duplicated this 50 samples which are there, and we have taken them to 950. So now we are having equal class 50 50, 950 in each of the classes. So this is showing the Python implementation. Anyways, I'm going to show it to you separately. You have to understand the concept. We have taken the random sampling first, and then it is SMOTE. Sorry. So synthetic minority oversampling technique generates new minority samples by interpolating between existing ones. So what is this synthetic it's not duplicating simply. What you are having random sampling. Random sampling is actually duplicating the current samples that are available, and it is taking to a different figure. But in SMOTE, it is not like that. It is in fact, this synthetic minority or sampling technique generates new minority samples. It is generating new samples wherever it finds, interpolating between existing ones, which are, it will be fitting them, interpolating and fitting them in between the current records which are there. And what will happen with this? Select a minority class sample and then find k nearest minority neighbors, create synthetic points along the segments. So formula for this is, so that has been given. Python from imbalance. So this is in fact the Python code which is there. Anyways, we are going to take it, but you need to understand the logic. I'm going to show you the program directly after this. That one program which is handling with, which is taking care of SMOTE. Then we'll be discussing the other technique in the next episode. So as far as the synthetic minority oversampling technique is concerned, it is just checking first of all the minority class samples, and then it is finding the k neighbors which are there, minority neighbors which are there. That means the points which are there where you are not having any class there, any data between those points which are already existing. So it will be fitting the new data in those points which are blank. So that is done. In fact, I'll be showing you directly now the program which is there, and it is using the SMOTE itself. Synthetic minority or sampling technique. First of all, it imports various libraries. I don't think I need to just again and again say the same thing. Then we are having one aspect of it. If you just see that we are creating the imbalanced dataset that has been created here. You just see we are taking weights of 95 and 5, which is a typical example of a we have discussed that it is a minor or you are having an average problem, you are having a less problem, low imbalance, average imbalance, and then there is a very high imbalance in the data. So here it is a high imbalance data which we are taking into consideration. You can just see weightage we have given 0.95 and 5. So minority class here will be 5%. 95% majority class, 5% of minority class. So this is how the data is created. And then we are putting that original class distribution, and then we are putting and displaying this. And then we are applying the decision tree classifier on this. We are fitting this model. If you're just training a model on this, we are splitting the data, and that is something we have taken multiple times. Data and data separate. We are doing train and test. We are taking that 3070 here as well, and random state 42, which is taken. I have given sufficient explanation for this pre, and then we are putting it to the decision tree classifier, and then we are predicting before our sampling. We are putting the results out. So we are putting results out here before our sampling, and exactly one thing which is very important, AUC score is something very important, because precision and all, it might not be making much of a difference. As we are having majority class as 95, even if model is not doing anything, the accuracy of 95 is going to come. So that's what we understood what is actually data imbalance and how it is impacting. So 95% of the accuracy will be directly done even if the model is not doing anything. So that is, we don't have to see that particular aspect. What we need to see is the AUC score. AUC score will be in fact designating whether we are having some improvement on the previous simple data and the when we are applying a synthetic minority or sampling technique. Now we are applying this SMOTE on the same data. So we are training it with the synthetic minority or sampling. So you can just see this here. SMOTE is equal to SMOTE random state, and then training, and then printing after SMOTE. So we are printing these values after applying SMOTE, and then we can just see here applying classifier, decision tree classifier, and then we are printing this after our sampling has been done, and we are printing the AUC score, which is very important. Now we need to just see what is the AUC score before applying SMOTE and after applying SMOTE. You might not be having much of a difference as far as the accuracy is concerned, but we need to just see, because that is the critical criteria, that AUC will be reflecting whether the minority class was addressed by the model or not. So that is something very critical, and we are putting it here. SMOTE, we are apply the SMOTE oversampling. So we are doing that here. Then we are training model with that, and at the end we are printing the values. So let me just run this particular program. First of all, let me get this results window a little bit up, and then I will just say run without debugging, and it is going to run this. If you see, we'll be getting results in short while. So here we go. Original data classification is we were having majority sample as 947 and we were having minority as 53. So total 1000 samples were there. 53 was minority and 947 was majority. And then we are getting this as a precision 97%, recall and other things. If you just see AUC is something which is very critical. We are getting 78% in this. You might be having other things, up to the mark, you can just see. But you see, AUC is something where we will be getting the difference, whether the minority has been taken into consideration or not. After SMOTE classification, we are putting now the data as 667 and 667 equal. Now you can just see after our sampling, although our precision has, in fact, it has, in fact, improved a little bit to the normal one, 97, 90, not much of a difference, but you can see a significant difference, I would say. Significant difference as far as AUC is concerned. So it has gone from 78 to 81%, which is a huge improvement in this, because the minority class itself is represented by 5%. So it's a 5% minority class. If you are having 2 to 3% of increase in AUC, that will be in fact reflecting that minority samples have been taken into consideration. Wherever you were having, for example, the minority which was coming, because otherwise the model was directly taking it that it is one class, so it was getting, for example, 95% the accuracy, or slightly higher than that. So simply it was take, but when it considered the minority class as well, we were able to improve this AUC score to a significant level, and this is reflecting that how our sampling techniques can improve your machine learning model. And exactly, it is not just about one aspect of precision or accuracy. It is about some other certain other critical aspects which will be otherwise rendering a machine learning model useless if we are not doing that. So that is what is shown with this example. In fact, I'll be providing you, examples, practical implementation of, one more technique which is there, but that will be happening. It is going to happen in the next episode. We will be having adaptive synthetic sampling. So ADASYN will be there, which is a different technique than SMOTE, and we will be seeing that adaptive synthetic technique which is there, sampling which is there, how it is different from SMOTE and what kind of advantages it's providing with a practical implementation on that. Thank you so much for joining this channel, and I hope that this will be providing you some benefit. This particular platform is intended to help students. So it is intended, in fact, the motto behind this is so that we can provide certain technological advancements that are happening, for example, AI and machine learning this time around, and cyber security. These are certain fields which are, this time around, where a lot of change that is happening. These are evolving fields, and artificial intelligence, machine learning is, it is revolutionizing every field or the domain. To get that expertise, so these channels are intended for that purpose, so that it can help students. The access to all information is free here. So this is just with an intention, so that we can help the students community, researchers, and others who are interested in this. So this can be a help to them. So with that intention, this particular channel has been launched. Thank you so much once again for connecting. If you're having any suggestions for this so that we can improve it, you're most welcome. You can just give your comments in the comments box, and we will be just trying to incorporate those changes and suggestions so that we can improve for future. Thank you once again for connecting.